Hello, everyone. Do you hear me in the back? Yeah? All good? Okay, so this is my very first time at this event, so I'm quite excited, but also want to thank the organizing committee for this opportunity. We can get started. The title of the presentation is Top-Down Excavation System, an integral solution for challenging deep excavation problems with complex surroundings and difficult geotechnical conditions. These are the contents of the presentation. So we'll begin with the basic principles, then move into the analysis and design. Afterwards, I'll speak about the construction aspects. Then I'll show you a few successful projects. And finally, I'll end with some takeaways. So why a top-down? That's the main question, right? I would say that because it's an integral solution that incorporates the deep foundation elements, the earth retaining system, and the excavation works. Plus, it also reduces urban impact because now we have an enclosed work environment with much less noise. And you can basically forget about having to invade the sidewalk or even closing down a street to park an excavator or your dump trucks, whatever. So you get rid of that problem. What else? No anchors, tiebacks, or struts for the retention because now we rely on the slabs for this. Another reason is a possibility of a simultaneous superstructure, which can be very attractive because that means that not only will we fully finish the basements by the time we complete the excavation, but we may also be able to build a portion of the superstructure, which is what's depicted on this figure. In terms of its applicability, the top-down is an excellent solution if your project has any of the following issues. So if you have deep or sensitive neighboring structures, then it makes sense because you might have some strict tolerances in terms of settlement or displacements. Another one is if you have complex geometry or a limited surface, because unlike in an open pit excavation, you are no longer limited to a depth that is set by the slope of a ramp or the reach of an excavator. If you have nearby utilities, such as electrical or gas, you don't want to hit that like while installing anchors, for example. Similarly with tunnels, we don't want to disturb those structures. If you have a high water table, because this solution has a watertight wall, so it can be designed to resist water pressure. And the last one is if you have soft soils, so for example, expansive clays or peat materials with low strength, high deformability, then you definitely want to look into this solution. Now moving into the analysis and design. First off, the earth retention, essentially a diaphragm wall. So this is what we typically would do. We would have an analysis model. This is a screenshot of, this is our in-house soil structure interaction software based on the reaction modulus method. However, if we come across a more complex project, we would definitely rely on a finite element analysis model. I'm sure we all know the advantages of this. In relation to the slabs, so these will be the elements transferring the lateral earth pressure and stabilizing the D-wall, so these are very important. And here I'd just like to stress that when analyzing these elements, we have to consider both the excavation and service loading conditions. Another vital element for the solution is the vertical beams or plunge columns. So these have to be designed for buckling. We also have to design their mechanical or welded connections. And of course, the load transfer node, That's critical. Now moving into the construction, beginning with the deep foundation elements. These are generally circular piles or barrettes. In either one of them, verticality is, vertical deviation is really critical. We really need to take care of that because that can make or break the installation of the vertical beams that we saw on the previous slide. So that needs to be accounted for in the design and not only the bearing capacity. Yeah, here we have a diaphragm wall. So in this figure, we can see all the required equipment to build one of these. But the most important tool is, of course, the excavation tool. In this case, we have a hydraulic grab. More on the D-wall. So here we have a few pictures to illustrate the excavation tool. Some quick facts about D-walls. Their thickness can vary between 0.5 and 1.8 meters. We have mechanical grabs, hydraulic grabs, and hydrophrase. Historically, the first one was the mechanical grab. However, I think that nowadays, the most commonly one is the hydraulic grab, just because of its verticality control and because it has more power. On the other hand, the hydrophrase is perfect if you have harder ground or if you need to excavate even some rocks that can be used. There's also an electrical version of the hydrophrase. Here we see how a reinforcing cage looks like. So these are, their design is tailor-made for site-specific geotechnical conditions, of course, but then it also accounts for the construction sequence, because that's also important. And it's always recommended to have monitoring during the excavation works. So here we can see a plot from an inclinometer, and we can use this data to compare against our analysis model, of course. We can calibrate soil parameters as well, so that's super useful. Verticality control, that's critical during the excavation of a D-wall. So we can accomplish verticality close to 0.1 and even lower, and that's at tip elevation, so at depth. We can also have real-time monitoring, and we can have corrective actions while we're excavating. To better illustrate that, we have this lower picture where we see the available controls for the grab operator. And yeah, the last thing I want to say about this maybe is that you can also verify the verticality of these elements by means of an ultrasonic echo sensing system that's also known as a CODIN. In terms of the panel joint, this is another very important point for diaphragm walls. So we achieve water tightness by means of this patented CWS formwork. This essentially is a temporary element that allows for the installation of a PVC or neoprene water stop along the entire joint between panels. But then it also provides or ensures contact between adjacent panels, so it has a double purpose. Another key element for diaphragm walls is the drilling fluid. So this guarantees the stability during the excavation of a D-wall, the stability of the inner walls. And this can be done with either polymer or bentonite. This is a material that's made on site, and it's constantly under quality control. So we measure its characteristics like density, viscosity, water content, filtration, the cake thickness, that's very important. Concrete-wise, D-walls require a special concrete mix, of course, but most importantly, it needs to be self-compacting. We also need to take care of the placement time to guarantee workability during the concreting phase. And this concreting must always be done using tremie pipes. That's to avoid any cold joints. The capping beam, so this is another very important aspect of a D-wall. This is a continuous element that ties all the D-wall panels together. In these two pictures, we can get a better idea of the size, the geometry, as well as the reinforcing density that this element can have. So this can be custom made to accommodate any loads or basal shear, distribute forces to adjacent panels so that they can be not only an earth retaining element, but also a bearing element, actual capacity. In terms of the working platform slab, this is where all the actions happens during a top-down. So it's a very special slab. It's not your average slab, as you can see. This needs to be designed accounting for very considerable loading during construction. Now some successful applications, some successful projects I want to share. We start with this 50-story high-rise. This is located in an actively seismic region. Here the project had a 1 meter thick D-wall with a tip elevation at minus 55 meters below grade, whereas the deep foundation elements had a tip elevation at minus 64, so quite deep. The project was for 7 basements of underground parking. And here we have more pictures for the same project. We can see the first one is for the capping beam, which was a massive one. It was really big. And the picture below shows the underslab excavation that reached a depth of 25 meters below grade. Yeah, just as a reference, the maximum PGA of 0.32 Gs recorded once the entire structure was already in operation. And on this slide, we can see the simultaneous superstructure for the same project. And we can appreciate the logistics in the working platform as well. So ultimately, this resulted in time savings, naturally. So it was very attractive for the clients, the owners. Another interesting project is this one. This was a 2 30-story high-rise buildings. So we had high-rise 1. What is it? Oh, yeah. High-rise 1 with 8 basement levels, and then high-rise 2 with 6 basements. The same owner already had this existing high-rise with 4 basements, so ultimately he wanted to join all the basements. That was accomplished in the end. But then the tricky part, or this is an example of a project with complex surroundings, because we also had buildings in operation with 4 and 6 basement levels, as well as this metro tunnel crossing that directly intersected with one of the projects, so the one below. For that, we see this elevation where we had the metro tunnel section traversing across the project, and that implicated that we had 2 diaphragm walls. So we had one along the outer perimeter, let's say, and then we had one inside because the basements, the footprint of the basements was reduced. So it shrank just to avoid the tunnel. That was an interesting one. And for high-rise 1, we had another concern that was that this basement, this existing basement had a somewhat thin wall that was not originally designed to resist the pressure from the concrete column when we are concreting the the D-wall for our project. So then the solution that was proposed was to have a concreting sequence of 2 stages so that we didn't have that much pressure on the neighbor's wall. That was done along the entire perimeter of that property line. Here we see a bird's eye view of this same project. So this is the one with the 8 basement levels. It had 2 large excavation shafts just so that the productivity during excavation was improved. And on the left, we have a picture of the vertical beams for the same project. So these are the vertical or plunge beams I was mentioning before. We see the load transfer node here for all of them at each level. These are embedded in the deep foundation elements. And this excavation reached a depth of 33 meters below grade. It was one of the deepest ones, although the record-breaking one I know of is 16 basement levels. So that was a very deep one. This other project I want to share is a large excavation. This is located in the US. This was for 2 entire city blocks, so it was a really large surface. The project was for a 6-story high-rise, so it's not such a big structure in terms of the height. But it did have an excavation going to 18 meters below grade. Here the D-wall had multiple tip elevations, similarly to the piles. During this project, the construction crew had multiple challenges along the way. Some of them were that they encountered boulders and cobbles, so they had that experience impacting their productivity rates. But then they also had to remove debris and contaminated soils. So it was a challenging project. And the reason for a top-down in such a large surface, because you may be asking yourselves, it would have been better to just have an open excavation, was that there were some heavy restrictions with soil anchors, so they couldn't place any high-strength anchors, tiebacks. And there was also the proximity to a rail line, so that was also a big restriction that resulted in the decision to have a top-down for this. Yeah, so some key takeaways for this presentation. Just wanted to say that the top-down is an integral solution that reduces urban impact. It has a definitive watertight structural wall that is built with strict verticality control, and it requires no additional cast-in-place wall in front of it. Plus, it also gives the possibility of a simultaneous superstructure, which can be really convenient and may result in time and cost savings. So this was a quick introduction to the top-down excavation system. It was all you need to know in under 20 minutes, but hopefully in the very near future, we can showcase a case study for top-down here in Vancouver. And I just want to close with this phrase that the top-down excavation system, the intersection of novelty and familiarity, it's something new, but it's something that we all understand. And yeah, now I can answer any questions, but I also wanted to share this quick video in the background to tie everything together, give a better idea, illustrate the solution. But you can ask away anything while we're at it.
Thank you very much. Very good presentation. I assume the first project were in Mexico City?
Yeah, right guess. Yeah.
Yeah.
One price.
One question is, in this top-down construction, My understanding is that you first basically build the pile foundations to support the columns, right?
Yes.
Down. The question I have is, if we need to build shear walls, right, to take the seismic force of the building, how do you support those shear walls before you go to the last foundation slab and connect those shear walls? How do you support those walls? On piles too, or?
But you mean internal walls or along the perimeter?
No, the walls in the building.
For the core.
All the seismic force.
For the core.
Tower, for instance, the tower has a shear wall that takes it.
Yeah.
Can you design the building shear wall for this type of construction, or is only typically frames?
Yes, that can be designed. We can accommodate a shear wall. They can, I assume you're talking about the ones in the cores mostly.
Yeah.
So those ones, for those, we generally solve it with this big foundation element. So it would be a barrette. This it's the opposite of the circular piles. So it's more of a rectangular shape. And it's really, I don't know if it's seen here, but it can follow the geometry and the shape of your core wall. So that's going to be the foundation element for the wall. And then we would install these vertical beams, these plunge beams, inside this deep foundation element within the dimensions or the thickness of this shear wall. And as we go down, we're tying each basement slab level with this transfer node that we generally call like a stump. And then as we go down, we are also placing all the rebar, all the reinforcing that is required for a shear wall to resist basal shear. No worries.
Any other questions? Thank you very much, Mark. Token of our appreciation.
Thank you.